Before we get started on today's material, I want to talk for just a moment about phase transfer catalysis. It was on the PowerPoint, but I want to mention it just a little bit. Let's suppose Gabriella comes into the lab and she wants to react this alkyl iodide with sodium cyanide to make a nitrile. The reaction itself, at least on the board, is quite straightforward, right? Cyanide acts as a nucleophile, an SN2 reaction. You end up forming sodium iodide as a byproduct, and you get the organic product that you want. However, if we think about this mechanism very, very closely, this arrow pushing is telling us how the groups have to come together to react. They have to come together to react, right? Let's think about these two reactants. We got an alkyl iodide, which is soluble in organic solvents but not water. And we've got a salt, which is soluble in water but not organic solvents. So how do we get the things to mix together? Turns out to be a bit of a problem, right? So if you imagine having a flask set up, bad drawing, right? And we've got an organic solvent, say something like methylene chloride, which is very dense, and something like water, which is less dense. We've got two layers, right? So when Gabriella puts her reactants in, what she'll find is that in the organic layer is the alkyl iodide, and in the aqueous layer is the sodium cyanide, and the two shall not meet. Creates a bit of a problem, okay? However, we can imagine a situation where we use what's known as phase transfer catalysis, which will allow us to transport the nucleophile from the water layer into the organic layer so that the reaction can occur. Basically, what we have to do at the fundamental level is make that salt organic soluble. Okay? Now, phase transfer catalysts come in a couple of different flavors. One is the so-called quat salts, where you have quaternary ammonium halides. Okay, that's one version. And let's talk about that. So let's imagine that I take this, and we got these big greasy R groups on there, 6 or 7 carbons for each one of them, and I place that in solution. It turns out that they have some solubility in both layers. Okay? Because it's a salt, it is water soluble, but because they also have these organic groups hanging off the nitrogen, they also can exist quite nicely within methylene chloride. So what happens? How does this work? So we've got sodium cyanide, right? And I've also got that around, right? So what can happen? Okay. That's right. So in solution, these are separated, right? And so you've got sodium cyanide, but they're floating around, right? And you've got ammonium halide, and it's floating around. And every now and then what happens is these get close enough to one another, and they're close enough to the surface where they can transport through to the organic layer. And now that's where the reaction can happen. That's right. And so, but this can go back and forth between the organic and the aqueous layer. Okay? Kind of has a special place in my heart because it was developed in my home state of Oklahoma at, I believe, Conoco or Phillips. I can't remember exactly which one. I think Conoco is where it was developed, this idea of phase transfer catalysis, because you need to be able to take one phase into the other so that you can do a lot of this chemistry. Again, very easy for us to show this on paper, but in practicality, this was not a straightforward reaction as you might think. You got to have some way to get the two layers together. Another way in which we can do phase transfer catalysis, the quat salt method is by far the most famous version of it, but the other one is using a special ether that we talked about in the last chapter, crown ethers. What do crown ethers do? That's right. So you can use a crown ether and I'm going to draw a bad one, okay? But imagine that being a crown ether. It can encapsulate that cation and complex it. We showed that where we could separate potassium from lithium, for example, right? How does this do phase transfer catalysis? It makes that cation organic soluble, right? It puts a lot of organic around it, and then now you can pull that down, that salt down into the organic layer and do the chemistry. And it is soluble because of all the oxygens in both layers as well, okay? So phase transfer catalysis is a very important thing from a practical standpoint in the laboratory. And I wanted to spend a little time talking about it. So today we're going to get into Chapter 12. We're going to talk about oxidation and reduction in organic chemistry. We're going to talk a little bit about how we can get alcohols through the process of reduction. At this point, we've made alcohols by the addition of water, right? We can add water to alkenes, for example, in both a Markovnikov and an anti-Markovnikov fashion. But we can also get alcohols by a process of reduction where we take carbonyls and we can actually add hydrogen across the carbon-oxygen double bond somehow and get alcohols. And so we can also oxidize alcohols to carbonyls. So we're going to learn a lot of this chemistry this chapter. From what you know from general chemistry, what is reduction? Gaining electrons. And what is oxidation? The loss of electrons. And it turns out that it's exactly the same in organic chemistry, but we don't count electrons explicitly most of the time. We have an easier way to think of reduction and oxidation. We look at a carbon atom and we go, does it have more hydrogen or less hydrogen than when it started? If it has more hydrogen, it's reduced. If it has less hydrogen, it's oxidized, okay? Now we're going to actually go through and calculate some oxidation numbers and learn that because it's very important when you get into biochemistry. A lot of what's going on in biochemical metabolic processes is oxidation and reduction. So it's very fundamental that you understand the oxidation states of carbon, and so we'll cover that today in addition to making alcohols and oxidizing alcohols. So I'm not going to go over this. At this point, you should start to have a lot of roadmaps put together. This is just a small one. These are all things that we've already talked about. And today it's going to get even bigger. Okay. Another thing that I want you to know, you can get this, of course, you can download the PowerPoint, so I'm not handing this out. But I want you to work these sample problems, and next week, on Monday, I will post the solutions outside my office up here. Not my office downstairs, but my office up here. And you can come by and look at it. And I promise you that right now you have all the tools to do these reactions. Every one of them. But have I taught you how to take one alkene and make another? Not explicitly, but you have all the reactions at your disposal to do that. Okay? Have I shown you how to make a dihalide that looks like this, where one halogen is bromine and one halogen is iodine? Nope, but you have all the tools to do that. Have I taught you how to take an OH and move it from one area and put it on another? Nope, but you have everything that you need to do that. And then number 4 is just working through a problem, okay? So these I have not explicitly taught you how to do, but you really do have everything that you need to do that. And I want you to spend a little time struggling through these, okay? And it's okay, all right? You need to get to where you can access the tools, the mechanisms that you have right now to do things that you've never actually seen before, okay? That's where the deep learning in 256 comes in, okay? So carbonyl group, of course, we know what that is, right? It belongs, or it's the C double bond O, and it belongs to a variety of functional groups, right? We can have a carbonyl and an aldehyde, a ketone, a carboxylic acid, an ester, of course, amides as well. They're just not shown up here. And so we know we have this carbon-oxygen double bond. One of those bonds is a what bond? One is a pi and one is a sigma. Which one is the weaker of the two? The pi, right? The pi bonds are always weaker than the sigma bonds. And so since we have these weak pi bonds, we should be able to do some chemistry with them, okay? And it turns out that the carbonyl is very good at doing a variety of different types of chemistry. So we can do chemistry on aldehydes, ketones, carboxylic acids, and esters, okay? And a lot of what we can do is actually oxidation and reduction. So for example, if we look at our, what is that, lime green kind of colored alcohol here, right? We can oxidize it to a carbonyl. What have we formally removed in that oxidation? We have removed two H's, that's right. So we've removed a molecule of hydrogen. And in doing so, we have removed two sigma bonds and replaced it with a pi bond, okay? So in theory, we can do this type of chemistry. Conversely, we can also take a carbonyl and reduce it by adding an equivalent of hydrogen, okay, to give us an alcohol, okay? Now it turns out that the carbon-oxygen double bond has some similar chemistry to the carbon-carbon double bond, but not everything, okay? Tell me in your mind right now, why is the carbon-oxygen double bond not like a carbon-carbon double bond? Okay, and so that there are resonance structures that we'll talk about, but there's not a different number of resonance structures for, okay, yeah, there are some different resonance structures. There's definitely electronegativity, and the bond is more polar, right? If I take two carbons and they have the same groups attached to them anyway, that carbon-carbon double or carbon-carbon double bond, not very polar. And in the IR, did that give a strong absorption or a weak absorption? A weak. But what about the carbonyl? It was a very strong absorption, right, because of the electronegativity difference, the polarization that changes as we stretch that bond, right? So, or the dipole moment, I should say more specifically. Okay, so oxidation and reduction, we can think about it in organic terms as the addition or the removal of hydrogens from a carbon atom. Okay? Some basic things that you all know. This is a trigonal planar carbon atom, right? We've got three groups all lying in the plane. We've got about 120-degree bond angles. We know that the carbon-oxygen bond is polar, much more polar than a carbon-carbon double bond, right? The carbon takes on a partial positive charge. The oxygen takes on a partial negative charge because of what Aubry was talking about, the electronegativity difference. And it's that dipole that gives rise to the strong IR absorption in the IR spectrum, right? And we notice, again, the 120-degree bond angles, regardless of whether or not we're talking about an aldehyde, ketone, or an acid or an ester. Okay, it's about the same. And so the carbonyl is a group within various functional groups. Okay? Now, if we think about it, there are similarities in the fact that a carbon-carbon double bond and a carbon-oxygen double bond both have a sigma and a pi, but the resonance contributors are actually quite different, okay? Yes, this is the major contributor, just like a carbon-carbon double bond is a major contributor, and this is the minor contributor, but would this contribute more to the carbonyl or less to the carbonyl as opposed to what we see in the carbon-carbon double bond? A little more, right? Because this makes some sense. Carbon taking on a positive charge, oxygen taking on a negative charge makes more sense, right? Carbon's more electropositive, oxygen's more electronegative. Makes some sense. And so even though this is a minor contributor to the overall resonance hybrid, it does account for a lot of the chemistry that we're going to see. So if you think about it, if we're going to add a nucleophile to a carbon-oxygen double bond, which atom, the oxygen or the carbon, will the nucleophile attack? The carbon, and why? Because it's partially positive. That's right. We will not have the nucleophile attacking the oxygen atom because we're going to have something that's negative coming around those lone pairs, or something that has those that negative charge associated with it, this contributor, right? So it's this minor contributor again that's going to be responsible for a lot of the chemistry that we're learning in these chapters. Okay? So if we take an alcohol, so here we have, what kind of alcohol would that be? That is a primary alcohol. We could oxidize it to a variety of things, but here we've got an example that is a carboxylic acid. Okay? So we have removed hydrogen and added oxygen. Notice that in this bracket we put an O. That is the abbreviation for oxidation. That does not mean we are using a reagent that is just O. That's a general reaction of oxidation. We're going to learn reagents that give rise to these types of oxidations. But if I was to write something on a paper and I wrote an alcohol O in bracket to something else, I'm just telling you, you're doing an oxidation, okay? Likewise, putting a hydrogen inside brackets is doing a reduction, okay? And so that is the general symbol that we use for reduction. So it's a shorthand. Instead of me writing reduction, I'll write bracket H, okay? And so on your road maps, you can do that. You can have bracket H and then figure out what all the reagents are somehow else. Okay? Calculating oxidation states. When you were in general chemistry, this probably drove you crazy, trying to calculate the oxidation states. It's actually quite easy for us in organic chemistry. It's very easy to count the electrons. We don't have to count to a very high number. You can actually do it on one hand, right? So it's kind of nice. We're not dealing with any of the transition metals and large numbers of electrons, okay? It's very similar to how we calculate formal charge, except in formal charge, we assume that all bonds equally share electrons, right? Which is a falsity. Okay? So, we are not going to assume the equal sharing of electrons. The most electronegative atom gets the electrons assigned to it in that bond. So if we have a carbon-oxygen bond, those two electrons in that bond are completely assigned to oxygen, okay? And then it's just valence electrons minus assigned electrons equal oxidation state. Very simple, okay? So if we think about ethanol and we look at this carbon, right, we're going to have to assign it an oxidation state. How are we going to proceed? These electrons, right, all belong to oxygen. These electrons belong to carbon. Carbon is more electronegative than hydrogen, okay? And then here, carbon and carbon both have the same electronegativity, so they're going to, this bond, one goes to carbon, one goes to that carbon, okay? So the oxidation state, if we go through, we have 4 valence electrons for carbon, right? And it formally, or has assigned to it 2, 4, 5 electrons. This carbon is in the -1 oxidation state. Okay? Is that a highly reduced form of carbon or a highly oxidized form of carbon? It's kind of in the middle. Okay? You'll take it. You think about it, methane, CH4, what would the oxidation state for methane carbon be? It comes in with 4, and how many total electrons does it have assigned to it? 8, so it is in the -4 oxidation state. That's as high as we can get in oxidation. Carbon with 4 hydrogens is as reduced as it can be. How about carbon dioxide? How many do we Yeah, that's right. It comes in with 4, 0 are assigned to it because everything's bound to oxygen, right? So it has a +4. So carbon can have anywhere from a -4 oxidation state to a +4 oxidation state. It has a wide range of oxidation states available to it, okay? And -1's kind of in the middle.
+4 would be highly oxidized? Or
You tell me.
I would assume highly oxidized.
Why do you assume that?
Because its oxidation state are going positive.
Okay. It's a little weird to think of it that way.
But it's correct.
If reduction is electrons, right?
So it's be negative.
Negative would be a higher reduced state, whereas more positive would be a less reduced state. Kind of same thing, but whatever works for you. Okay. So I want you to calculate for me the oxidation state of each carbon in these 2 molecules. So the carbon in methanol and the carbon in formic acid. How do we calculate it? Let's look at methanol. What do we do? So it comes in with 4, and how many do we assign to it? 6. Is that more or less reduced than ethanol? That's right. It is in a higher oxidation. It is in a more reduced state. How about for the formic acid? Yeah. So we can actually calculate the oxidation state of carbon in these molecules very, very easily just by assigning electrons. Very similar to what we did in formal charge, except we are throwing out the formalism of equal sharing. Okay? So which one of those would make a better fuel in a car? Which one? The one that's more oxidized? So if I'm going to take, I want reduced, right? Because that's right. So methanol actually is used in Indy cars. That's the fuel, not formic acid. This is in a more reduced state.
I was thinking octane and oxidation, and got this, it was like, ooh, that's not right.
Yeah. And by the way, octane really has nothing to do with octane. Just to let you know. It's right. Has to do with what's known as isooctane. Normal octane is actually a horrible fuel. So let's imagine some generic reactions that we can do with carbonyls. We've just established that the carbon-oxygen double bond is polarized and that the carbon atom is partially positive, right? So in theory, it looks like it should be possible to take a nucleophile that has a negative charge and attack the carbon of the carbonyl and break that weak pi bond, getting what we call a tetrahedral intermediate. So we go from a trigonal planar starting material to a tetrahedral intermediate, okay? The arrows are very, very simple. This is very similar to what kind of reaction? Very similar to an SN2 reaction. The nucleophile comes in and attacks. The leaving group leaves. Just so happens the leaving group is a pair of electrons and it stays on the oxygen, okay? That's not a perfect analogy, but it works pretty well. And we break that weak pi bond. Is this going to lie to the right or to the left? To the right. And why to the right? I am forming a bond. What kind of bond? Okay, I'm forming a strong sigma bond at the expense of a weak pi bond. And so the reaction lies to the right. And in fact, they do not draw this one as an equilibrium at all because it lies so far to the right. Okay? There are some examples that we won't get into today where it does, it can go back pretty easily, but not in this particular case. Okay? So now we have an alkoxide. Then we work the reaction up by pouring it over ice water usually, and we end up getting an alcohol. So guess what we've just done? We have taken a carbon double bonded oxygen and we've converted it into an alcohol. Depending on what the nucleophile is, it can be a primary, secondary, or tertiary alcohol. Okay? And depending on what this group is. Okay? Very simple mechanism. You're going to find that in this class, the mechanisms are actually very easy. Okay? It's putting all the pieces together to get the final product that you want that's difficult.
Would it need to be a good nucleophile in there, or just like a relatively okay one?
It needs to be a decent nucleophile, and we'll talk more about that later. Okay. Now, some of the nucleophiles that we can use are hydrides, H-. Unfortunately, you can't just buy a bottle of H-. You have to have a counterion of some type, right? So you can imagine having sodium hydride. But it turns out sodium hydride is a good base, but not a very good nucleophile for reasons that we won't go into. However, sodium borohydride, which we've used before, where did we use that before? Oxymercuration, demercuration sequence. So after the oxymercuration, we threw in sodium borohydride to do what? Yeah, and so what were we doing to the mercury? Were we reducing it or oxidizing it? Were we? We were reducing the mercury. That's right. So we were reducing it. So it's a reducing agent. Okay? Now, if you look at the periodic table, you'll see that boron here has the formal negative charge, just by doing the formal charge calculations. However, boron is a metalloid. Are metals more electropositive or more electronegative? The more electropositive, right? And so it turns out that the boron-hydrogen bond is actually polarized such that the negative charge, partial negative charge, is more on the hydrogen. And so we can think of these as H- equivalents. How many H- equivalents do we have for sodium borohydride? We have 4. So for every mole of carbonyl, we only need 1/4 of a mole of borohydride. Sodium borohydride is a very, very convenient reagent. You can dissolve it in basic water. It's pretty stable. You can weigh it out in the air down here in southern Mississippi, not have too much of a problem. Its cousin, however, lithium aluminum hydride, is a bit more naughty. Okay? Very similar in terms of structure, except we've replaced the boron with aluminum, right? Aluminum is right under boron in the periodic table. So would we predict that this is more reactive or less reactive? More reactive. Reactivity typically goes up as you go down a family, typically. Okay? So lithium aluminum hydride, too, also has this polar bond, and so we can think of these as H- equivalents. But this guy right here is very, very energetic. If you put this in water, it bursts into flames. I can weigh it out in air if I'm quick. Okay? We do use it in my lab quite a bit. It's not that hard to really work with as long as you know what you're doing. But don't try to make a solution of this in water or any type of alcohol. It will go boom. Okay? So for example, we could take either one of these reagents and we could take an aldehyde or a ketone and we could reduce it. And then when the reaction's over, then add water and we can get an alcohol. So if officially we are adding H2 across the carbon-oxygen double bond. Okay? Where did this hydrogen come from? Okay, it came from the reducing agent. Where did this hydrogen come from? The water. That's right. We are not really adding H2 at one time. The mechanism is not the same as the reduction of an alkene. Okay? It is a 2-step process. That's exactly right. So let's talk about that mechanism. Let's do it over here. So let's imagine that Amber has an aldehyde of some type, and she wants to reduce that to a primary alcohol, and she's going to use sodium borohydride. Now, sodium borohydride is stable in water, so she does this in sodium borohydride water mixture. That's perfectly fine. Stir it up real fast. How am I going to push the arrows?
So we're considering the hydrogen negative now, correct?
Mm-hmm.
So from the hydrogen, the carbon to the carbon, that's the alcohol.
The way I like to do this for shorthand is I like to think of this as H- equivalents. There is no H- floating around in solution. It just makes doing the mechanism very, very easy. So I can have an H- attack the carbonyl, break the weak pi bond. I get an alkoxide, which then reacts with the water to protonate, and I get my product. Okay? In reality, it's a little more complicated than that. But if you can do this, I'll be happy. All right? Well, let's talk a little bit about the reality of it. How do I push the arrows? Do I do it from the boron? We're thinking of it as H-, right? So it turns out that the sigma bond actually moves. And then the pi bond reacts with the boron. That can go on and react with other and do this over and over again. Okay? So that's just one step. It's actually a much more complicated mechanism than this abbreviated mechanism that I'm showing here. This is what I'm going to hold you to. I just want you to understand that it is a much more complicated mechanism. Okay? So if you want to think of it, you're kind of adding a hydrogen and a boron across the carbon-oxygen double bond, which can do that 4 times. Okay? And then when you treat this with water, you actually hydrolyze off the boron, off the oxygen, and you end up getting your alcohol plus boric acid. Okay? In the end. So which mechanism do you prefer? Like the first one. So, for example, you need to commit this to memory. Aldehydes get reduced to primary alcohols. You need to know that by heart. If I come in and I say I want to make a primary alcohol, you should say you can make those from aldehydes, Dr. Masterson. All you got to do is reduce it. That's true. The reducing agent here can either be lithium aluminum hydride or sodium borohydride. Ketones give me secondary alcohols. And that makes sense because there's already 2 carbon-oxygen, or 2 carbon-carbon bonds there, right? So that makes sense. I get a secondary alcohol. Carboxylic acids, when I reduce them, I get primary alcohols. And esters, when I reduce them, I get a primary alcohol. I get a primary alcohol from the carbonyl anyway, and then you get this group, which was the other part of the ester, whatever it may be. It may be a secondary alcohol. But you get a primary alcohol out of the reduction of the carbonyl formally. Okay? This is really easy to memorize because all you got to do is say everything gives me a primary alcohol except ketones. Right? That's pretty simple. Ketones give you secondary alcohols. Okay? So let's look at some examples using sodium borohydride. So if Aubrey comes in and takes propanal in a mixture of sodium borohydride and water, what's the product going to be? Name it for me. It's going to be a primary alcohol. Which propanol? 1 propanol. That's right. We're going to end up with 1 propanol. Okay? Yusuf could come in and take a cycloketone, in this case cyclopentanone, reduce it with sodium borohydride. What kind of alcohol are we going to get? It's going to be a secondary alcohol, and name it for me. Cyclopentanol. That's right. I don't have to have a number there. Why do I not have to have a number? Yeah, no matter where I put the alcohol, it's the same name, right? We can also take an example where we have a ketone and an ester and reduce this with sodium borohydride. Here they're using sodium borohydride in a mixture of methanol and water. The methanol just makes everything nice and soluble. Okay, it's just an organic derivative of water. What product am I going to get? Okay. If I think of this as just simply a reducing agent, I should be able to get an alcohol here and here, right? But when Gabriella runs the reaction, she finds out that she gets the secondary alcohol from the reduction of the ketone, but the ester is left alone. Esters do not get reduced typically by sodium borohydride. Sodium borohydride reduces very nicely ketones and aldehydes, but it leaves carboxylic acids and esters alone. That's kind of nice. That is a selective reduction. If Olivia came in and said, you know, I really want to keep my ester, but I need an alcohol here, she's going to pick sodium borohydride. It works very, very nicely. Leaves the ester alone. Okay? Sodium borohydride is limited in its reactivity, and therefore it's a selective reagent. Okay? Which is very nice to know. Lithium aluminum hydride, on the other hand, a different animal. Notice here how it's written over the arrow. Lithium aluminum hydride in ether followed by water. If on an exam you write lithium aluminum hydride / water, it's wrong. Literally on the question anyway, right? Yeah, and maybe in the lab. That's right. Okay? It's very, very important that you recognize that these are 2 separate steps. Okay? So if we take cyclohexanone, lithium aluminum hydride, and ether to start with, we wait until all the lithium aluminum hydride has been consumed, then we dump it into water, we get cyclohexanol. So a ketone to a secondary alcohol, as we would expect. If we take an ester and we reduce it using these conditions, We're going to get a primary alcohol from this, which you can see here, and we're going to get the methanol as a byproduct, and we'll talk about that mechanism in a little bit. But notice here, we've reduced both the ketone and the ester, so we end up with a secondary alcohol and a primary alcohol. They didn't show, for whatever reason, the methanol, but it's there, okay? So, what do you think about carboxylic acids? If I take lithium aluminum hydride and a carboxylic acid, what do I get? I get a primary alcohol. Lithium aluminum hydride reduces all the carbonyl functional groups. Sodium borohydride does not. Okay? What, sodium borohydride? Lithium aluminum hydride we use when we absolutely have to, because it is so reactive. Okay? It's a heck of a lot more expensive. I can buy a bucket of sodium borohydride for the price of a small can of lithium aluminum hydride. Okay? We can leave it out on the bench top. We can do all kinds of stuff with sodium borohydride. Lithium aluminum hydride, we have to keep in a desiccator, keep the moisture away from it, all that kind of stuff. So it's pretty violent stuff. You will use sodium borohydride, yes. You will not use lithium aluminum hydride. Many of you it would end in tears. Huh? We really don't. We really don't. So sodium borohydride is the reagent of choice, even for a seasoned organic chemist. If they have a choice between sodium or lithium aluminum hydride, they always choose sodium borohydride. Okay? So now let's talk about the mechanism, especially as it relates to the ester. And we're going to use the abbreviated mechanism where we're thinking of it as hydride. But my hydride source is lithium aluminum hydride. Not all hydride is the same. So Amber, what's going to be my first step? Where? If I attack the double bond, I can attack it here, I can attack it here. Okay, very good. I'm going to break that weak pi bond, right? Is that a primary alcohol? It's not an alcohol at all. It's an O minus, but it's also got another OR on it, right? Is that the product? It is not. What happens? With what? I don't have water yet. Okay, so if I take more H minus and react with that tetrahedral intermediate, where would it attack? So you're thinking more hydride would come in and attack here and this would leave? Okay, that's not a bad thought. That's essentially what's happening, but not directly. Okay? Hydride's not a good enough nucleophile to come in and kick that out as a leaving group by itself. But what happens is that this tetrahedral intermediate is not particularly stable, and it collapses into an aldehyde and the alkoxide. Technically, this is an equilibrium, but the equilibrium lies here. Okay? I've got an aldehyde. What happens to aldehydes with lithium aluminum hydride? It reacts again. And now the second reaction happens. Got my two hydrogens from that, and I've got the R prime O minus. Nothing else can happen, and so now all my lithium aluminum hydride is consumed, and I dump it over water, and I get my products. Okay, usually we dump this over ice, not just water, because there's always a little residual lithium aluminum hydride present. So you want to keep it cool so it doesn't go kaboom. Okay. But this mechanism is new for you. This next step here is new. This is called an addition elimination. Notice we are adding a hydride and we are eliminating an alkoxide. It is an addition elimination. And in the process, we get an aldehyde intermediate, which will then go on and react with the additional lithium aluminum hydride that's present. Does it seem possible that if we control the amount of hydride very, very carefully, we ought to be able to stop at an aldehyde? If we're very, very careful, and it turns out there are reducing agents that can do that, and we'll talk about those later. Lithium aluminum hydride does not do that. It goes all the way. That's right. Even if you're trying to be careful with the equivalents, you just won't convert all of the ester to the product. But once you get a little aldehyde, it reacts with the remaining lithium aluminum hydride. So you really can't control it very well. Okay? So lithium aluminum hydride is going to take everything to an alcohol. That's what you need to know. Carboxylic acid, ester, aldehyde, ketone. Now there are some practical uses here. So for example, if you start off with this ketone, notice it's got an isobutyl group out here on this benzene ring. This is a commercial preparation for ibuprofen, stuff that you take after class, right? So you take your ketone, and they actually reduce this industrially using sodium borohydride and an alcohol. Not sure if they actually use methanol. They may. And you get this alcohol. It's a secondary alcohol. Very easy reaction to do. In fact, you guys are going to be doing almost this identical reaction in lab, except it's not going to have the isobutyl group. It's just going to be acetophenone. Okay? This reaction goes very, very nicely, very, very cleanly. The yields here are very, very high. And then through a few steps, they're able to convert this alcohol ultimately into Advil and Motrin. Okay? And so this is the first step in the industrial synthesis of that important pharmaceutical. Okay? You think ibuprofen's a big money maker? It makes quite a bit of money every year. A lot of people buy it. Problem is that everybody makes it, you know, and so the generic versions are there. So, you know, it's not going to float a company these days. But, you know, there are probably $1 billion or more in sales of ibuprofen every year total. But, you know, that's split up probably around 20 or 30 different companies that make it to try to get their piece of the pie. Another reaction, taking this ketone, notice there's also a double bond. What can you tell me about the reduction here? In theory, we could have reduced the double bond or the carbon-oxygen double bond, right? But what gets reduced? The carbon-oxygen bond, right? So this is a selective reduction for this particular functional group. You get the alcohol, okay, as you would expect. Since we're going from a ketone, we get a secondary alcohol. And then 4 additional steps that we won't talk about, they actually convert this alcohol into the odor of musk, okay? Huh? Yeah, it's just a solvent to make everything dissolve. This isn't soluble in water at all, so they add methanol instead of water, okay? And so you end up with muscone. Kind of nice to be able to synthesize this because can you imagine how many musks you'd have to kill to make a bottle of perfume? Yeah, we don't really want to do that, right? So we can make it synthetically. This is the molecule that gives that odor of musk that a lot of people like in their perfumes and colognes. And it's a very simple organic molecule. Does it have any chiral centers? It does. Yeah. And it turns out that they don't make this enantiomerically pure. They make it as a mixture, but the musk animal actually makes it. I think it's the S configuration. So half of it you really can't smell. Let's talk a little bit about oxidation of alcohols in the time that we have remaining. So we can reduce carbonyl compounds to alcohols. So we should be able to take alcohols, remove hydrogen, and get carbonyls. And in fact, we can do that very, very easily. If you take a primary alcohol and you oxidize it, you have 2 options. You can remove 2 hydrogens and get an aldehyde, or depending on the oxidation reagent you use, you can actually get carboxylic acids, okay? Because you have these 2 carbon-hydrogen bonds that can technically be removed. So we'll talk about knowing how you get an aldehyde or a carboxylic acid, okay? You can take a secondary alcohol and you can get a ketone. And that's all you can do in the oxidation that we're going to be talking about, at least in this chapter, okay? And tertiary alcohols, notice they have no carbon-hydrogen bonds. No oxidation can occur. So tertiary alcohol in the presence of these others. If you treat it with an oxidizing reagent, you'll see no reaction with the tertiary alcohol. A couple of reagents that you need to know are the chromium reagents. Chromium trioxide is a very good oxidizing agent for alcohols. It's got chromium in the +6 oxidation state. It's not soluble in organic solvents, so they came up with this one called pyridinium chlorochromate, which also has chromium in the +6 oxidation state. Works very well to make take primary alcohols to aldehydes. PCC will take primary alcohols to aldehydes. However, chromium trioxide will take primary alcohols all the way to the carboxylic acid. Okay. So we'll finish up with this on Friday, but I wanted to mention real quick where this was useful many, many years ago. So chromium, if you've ever seen chromium salts, they're kind of a reddish yellow color, kind of orangish in a way. And they used to use these as breathalyzers, okay? So breath scan, that's the chromium salt in there, and when you were done at the bar, you would breathe through it, and they would see how much it turned green, and they would determine whether or not to give you your keys or not. These were big kind of in the 80s when they were having the big pushes against drunk driving, 70s and 80s. The problem is these aren't very environmentally friendly. You would use it, you'd throw it in the trash, chromium would end up in the landfill, whatnot. And so we don't really use these today. They're electronic gadgets that do the same thing. But this is what Jones reagent looks like. Jones reagent, you need to know that by name. It's just a mixture of chromium trioxide and sulfuric acid and water. It's kind of this orange color. And then when I added some absolute ethanol to it, it turned green. And so that's how you know that the reaction's over. We love these reactions in my lab because you just watch the color. When it turns green, it's done. Green means go. You go on to the next step, and you're done. All right, we'll pick up with more on that on Friday. Please turn in your inverted lecture up at the front.